You know that if the variable x is, for example, inside the radical, the result is called a radical function. If the x is going to be down the denominator, it's going to be a rational function. So if the x is going to be the exponent of a fixed number, in that case, you are going to have an exponential function, okay? So officially, if b is a positive number, if b is a positive, okay, a positive number with b not equal to 1, then an exponential function with base b, then an exponential function with base b is going to be defined by, f of x equal to the b to the x, but x can be any real number for all real numbers x. Okay, so it's going to be exponential function with base b or at base b. B cannot be equal to 1 because in that case you are going to have f of x equal to the 1, which is going to be a constant function. And b cannot be negative because you would like to have this function to be a real function. If b is going to be a negative, you have to bring the complex numbers, and that would be a different story. Okay, and again, a b cannot be equal to the 0 because in that case, again, this function is not going to be defined. So that's going to why this b must be a positive number and b not equal to 1. Okay, but so for example, if you like, for example, f of x equal to the 2 to the x is going to be an exponential function. Exponential function with b equal to 2. So the base is, base is 2. And or this function g of x equal to the 1/3 to the x, which is the same as the 3 to the negative x, is going to be an exponential function. Okay, an exponential function with base with b equal to the half. Okay, we're going to stay with this base, or in calculus, we are going to be interested in one very special function. So we are going to focus on this one. So in particular, if b is going to be equal to the e, you know that e is a number like pi, and you are going to see the e quite a lot in calculus 2 in this course, and you are going to see it in various formats through the end of the course. But for the time being, we are going to accept it as is. So it's going to be something like, it's like a pi, something like 2.731, etc. It's irrational number, okay, is an irrational number. If this is going to be the case, then f of x equal to the e to the x is going to be called the natural exponential function, okay, is the natural exponential function. All the other function can be changed into the natural exponential function. That's why we are going to work with this function only. And there are some other reasons that we have where we have to use this function, and we talk about it later on. Okay, so we are going to focus on this function, the property of this natural exponential function for this course. It's a very interesting function, and it's going to be used in various applications. So let's check some of the property of this function. So what is properties of the natural exponential function? F of x equal to the e to the x. The first property is the domain. Domain of this function is all real numbers, because we already talked about it. Because you can find any exponent you like. Of course, you have to use your calculator. Use your calculator anytime you want to work with the natural exponential function. Okay, so the domain is going to be R. So it's defined for all real numbers. The range of this function, okay, the range, you see E is a positive number. So when you raise it to any number, the result is positive. So the range is going to be all real, only positive numbers, 0 and positive infinity. Okay, because it cannot be, it's never negative. So this means e to the x is never 0, and e to the x is always positive. Sorry. This is going to be used from time to time. So make sure you remember it. So that's going to be domain and the range of this function. Some other property of this function that we're going to use, e to the 0 is always equal to the 1. So this means f of 0 is equal to the 1. And so 0, 1 is the y-intercepts. Okay, the y-int of the graph of y equal to the e to the x. And the other one is this function is increasing. Okay, so f of x equal to the e to the x is increasing. So this means as you increase the value of the x, the value of the function getting bigger and bigger. And two property that we're going to use from time to time, limit of e to the x when it goes to positive infinity. Since this is going to be increasing function, then it's getting bigger and bigger and bigger. So this would be eventually a positive infinity. Okay, and the limit of e to the x when x goes to negative infinity. So when the power is negative, this value is getting smaller and smaller, and eventually this would be 0. Okay, and then we can use this property to get the graph of the function. So this is going to be the graph of the function. The y-intercept would be at 1, and the function when x goes to negative infinity, this is 0. So it's going to be, this is going to be y equal to the 0, is going to be a kind of horizontal asymptote of the graph. And when it's getting bigger and bigger, the function getting, so this is going to be a positive infinity if you like, and this is a positive infinity. So you can use some, you can use your calculator if you like, or some numbers. So this is going to be the graph of the function, y equal to the e to the x, and this is going to be 1. Okay, so from time to time, we're going to use it. It's an exponential function. So we say that it's exponentially increasing function. Exponentially increasing means is getting bigger and bigger, bigger and fast. Like the growth of the coronavirus, for example. The growth is going to be exponentially increasing. Okay, and you invest money in the bank, so your money getting bigger and bigger and bigger. So these are going to be various interpretation of the graph of the e to the x, and we're going to get back to it from time to time. Okay, so this is going to be the case. Now the case 5 is the one that we are interested in. This function is differentiable. Okay, so f of x equal to the e to the x is differentiable. And that's why we like it. Differentiable, and the derivative of this function is the same as the function. Okay, so derivative of e to the x is simply e to the x. This is the only non-zero function with this property. The other function that you can find is just a zero function. If f of x happen to be equal to the 0, derivative of 0 is 0. But if you would like to have a non-zero function, this is the only one. Okay, so we say that the say the derivative of this function is never changed. Exponential function, exponential function. Okay, so this is going to be in general one, but you know that we can bring the chain rule and to get a more general format of this one. So in general, if u is going to be u equal to the u of x is a differentiable function, then by the chain rule, derivative of e to the u is equal to, you know that you have a composition of two functions, u function, e function, chain rule. Chain rule, derivative of the e function. Derivative of the e function is that's the e function. Multiplied by derivative of the u, which is u prime. Okay, so derivative of e to the u is e to the u, u prime. So if it's going to be e to the x, you end up with the e to the x only. If it's going to be e to the something else, you have to pay for it. And that's going to be the u prime. So don't miss it. Okay, so derivative, anytime we have the derivative, we can change it to the integral. So equivalently. Okay, equivalently, this is the integral of e to the x dx is never changed because you want to find a function whose derivative is e to the x, it's just e to the x plus c. But if it is going to be e to the u, integral of the e to the u, you have to have the du. Again, it's never changed, e to the u plus c. So that is all we need to be able to take care of these, these exponential function. Okay, make sure that you are able to differentiate it and make sure to integrate it for the rest of this course. We give you a couple of questions, differentiation and the integration in the coming quiz. Okay, and the problem that we assign in 6.2 are all of this, okay, this format. So that's all we need really. You can read the rest for yourself. So example, differentiation first, find the derivative. Okay, find the derivative of each function. Just give you mostly the one that we are going to use through this course. The first one is the one that you don't need any chain rule. So f of x is going to be a power of x, like x to the fourth, e to the x. Okay, this is a product of two functions. The first function is x to the fourth, the second function is e to the x. So we have to apply the product rule. Remember the product rule, first, second, is going to be derivative of the first one, f prime, times the second one, plus derivative of the second one, s prime, times the first one. Okay, so that's going to be the first. So that's going to be the first, and this is the second. So we are going to operate solution. So what's going to be f prime of x, derivative of the first one, derivative of x to the fourth is simply 4x cubed, times the second one, e to the x, plus derivative of the second one times the first one. Derivative of the second one is just e to the x, because derivative of e to the x is just e to the x times it by first. So it's going to be x to the fourth, e to the x, and do that. No simplification is possible. Some people try to simplify it. You can't simplify it. Okay, some people factor out e to the x. So what? It's already done. Okay, so this format is going to be used over and over and over in this course. Just make sure you know it. Derivative of the first times second, first. Of the first one would be 4x cubed times the second function e to the x plus. Derivative of the second times the first. Second one is exponential function. Derivative of exponential function is just exponential function. So that gives x to the fourth, e to the x, and you're done. Okay, that's a type 1. Type 2, the chain rule type. G of x e to the negative x squared is a very famous function. This is the one we use in a statistic. It's a normal distribution that you use, for the probability definition. Now, to find the derivative of this function, you see this is not e to the x, it's e to the something else. So you may think about it as, you see this is g of x, is e to the negative x squared, is like e to the u. So remind yourself that if you want to find the derivative of e to the u, you see, you have to use the chain rule. It's a composition of two functions, e function, u function. So it's going to be e function, e to the u, but times that by the derivative of the u, which is u prime. Okay, so what's going to be the solution? G prime of x is equal to e function is the e function, e to the negative x squared, but pay for it, u prime. U prime derivative of the top. Derivative of a negative x squared is a negative 2x. We usually rewrite it as negative 2x e to the negative x squared. So that would be g prime of x, negative 2x e to the negative x squared, and you're done. Okay, so the difference is, for the first one, you didn't need to use the chain rule, but the second one you do need. Okay, you don't need the chain rule because this is not e to the x, it's e to the something else. Okay, it's e to the u. So derivative of e to e function is just e function times it by the u prime. So we repeat the e function, e to the negative x squared, but times it by the u prime, derivative of the exponent. Derivative of a negative x squared would be negative 2x. So negative 2x e to the negative x squared is going to be the final answer. Okay, so, and the other form is a combination of both of them. This is the one that we are going to use most of the time. H of x equal to the 3x squared e to the, okay, e to the negative, let's say, negative 2x, 2x to the 4th. So to start with, this is a product of two functions. The first function is 3x squared, the second function e to the negative 2x to the 4th. So we have to apply the product rule. Derivative of the first easy, 6x times the second. But derivative of the second times first, it's an e function. It's not e to the x. It's e to the something else. So for the second one, you have to check it as a e to the u when you differentiate it. Okay, so the solution for this one is going to be h prime of x is equal to derivative of the first one, 6x, times the second one, e to the negative 2x to the 4th. Done. Now second first, plus. The second one is exponential function. Exponential function never change. It's going to be e function, e to the negative 2x to the 4th. But this is u type, if you like. So you have to pay for it, times it by u prime. U prime derivative of the top. Derivative of the top would be negative 8x to the 3rd. Okay, so derivative of the first one is ordinary differentiation. Second first, you have to apply the chain rule. E function would be just the e function times by the u prime. U prime derivative of the top, negative 8x. This derivative of the second times it by the first, times it by the first. Okay, then you have to simplify these two. So h prime of x is going to be equal to 6x e to the negative 2x to the 4th. Now multiply these two together, you are going to have a minus. 3 times 8 would be 24. 24x to the x squared times x to the 3rd would be x to the 5th. X to the 5th, e to the negative 2x to the 4th. The final answer. Okay, this is the kind of most general format that you can have. You see, compared with the first one, first one is very much similar. But when we get to the derivative of a second times first, you didn't need the chain rule, because the derivative of e to the x is just simply e to the x. But this one over here, when we go, we want to find the derivative of a second one. The derivative of the second one, the derivative of the e function is the e function, but it's not e to the x, it's e to the something else. So you have to take care of the u prime. Okay, u prime, but times it by the first. Then you simplify these two together and then you're done. So that would be basically the derivative of these, these exponential function. Okay, we don't need anything complicated. You'll be able to take care of these for us, you'll be fine. And you can check with this 6.2, a couple of differentiation that you have, maybe one of them in your next quiz. This next one is used a couple of places. So we just want to make sure you remember it. Okay, so nothing complicated, but just get to know it. It's a famous function. So for example, y equal to the e to the secant of x. You may have e to the sine x, cosine x, secant x. It's fine. Nothing to worry about. So it's u is secant of x. So to differentiate it, solution would be y prime. The e function is the e function. Is e to the secant of x. But it's not e to the x, it's e to the secant of x. So you have to pay for it. So the pay for it means you multiply by the derivative of the secant, u prime. If of secant would be secant tan. Secant of x, tangent of x. That's it. You can rewrite it if you like, but that would be fine if you want to rewrite it. You usually write the exponential one right at the end. Secant x, tangent x, times it by e to the secant of x. It's unusual, but there is a case for the exponential function that we are going to use in future. We need e to the cosine and e to the sine. There are a couple of problems in application in physics, and you will have this sort of function. So one just want sure that you remember it. So, and we are ready to use it. Okay, so this is all we need for the differentiation. Okay, so how about integrations? The integration of the e function will be quite a lot in chapter 7, but for the time being, we are going to just get to know it, with this format, and then we have more in future. So this is going to be our next job. We would like to evaluate each integral. Evaluate each integral. Okay, two format, ordinary one and the one with the substitution method. So for example, if you want to find the integral of, let's say 3x squared plus 5e to the x plus 2 dx. That's it. Okay. 3x squared plus 5e to the x plus 2. Now, is ordinary integral, nothing special. So integral of a 3x squared plus 5e to the x plus 2 dx is going to be equal to the first one. That's it, 3x squared, you know that. Is going to be 3, 1 up, x cubed over 3 plus 5 times integral of e to the x is just e to the x. E to the x never change. So that gives e to the x. And integral of 2 would be 2x plus the constant c. These two will cancel out. So the result is going to be what? The result is going to be x cubed plus 5e to the x plus 2x plus c, the final answer. Okay, this is a kind of, usual one. nothing special about it to get this number done. Okay, so that's type 1. The type 2 is mostly the one that we need to use substitution method. Okay, so start with this one, integral of x e to the x squared dx. That's a 1. You see it's not e to the x, it's e to the u because it's x squared. You check to see you want to use substitution method. You check to see if the u prime is here. Okay, if you take u to the x squared, so u prime would be 2x. You can use the shortcut or just the usual one, okay? So we try to change this one into the u to the e to the u. So the solution is going to be, you take the u to be x squared and try to change this one into the e to the u. So we find the du, which is going to be the 2x dx. We have to find the dx. The dx is going to be du over 2x. Okay, go back and substitute. If everything is all right, you must end up with e to the u. So it's x e to the x squared dx is equal to the, you keep the x, e to the, replace the x squared by u, so that gives e to the u. And the dx is going to be the du over 2x. So we simplify the x and x. The leftover is 1/2. You can pull out the 1/2. So you end up with the integral of e to the u du. And we know that integral of e to the u is just e to the u. So it's going to be 1/2 of e to the u plus the constant c. Then you substitute for u. So that gives you 1/2 e to the u. What is u? X squared plus the constant c. So the final answer, x e to the x squared dx is 1/2 e to the x squared plus c, and you're done. Okay, so because the only formula that you know so far is just the e to the u du. In future, we are going to have various methods related to this form, but this is easy and you don't need any other things to do. Okay, so it's e to the x squared. You try to see if you can change the e to the u. So we take the u to be x squared. U to be x squared, the du, you know that u prime dx. 2x dx. We find the dx would be du over 2x. We go back and we substitute. We substitute the x, we replace the x squared by u, so that gives you e to the u. And replace the dx by the du over 2x. X and x would cancel out. The leftover is going to be 1/2. 1/2 out, so we get e to the u du as you expected. And you substitute and you get the final answer. Okay. If you want to use the shortcut for this problem as we did it before, you see the shortcut, not bad to know. But you know, you can use this method all the time. The short form is, this is x e to the x squared dx. Remember, you need the u prime here, because the u prime dx, that gives you du. So your u is x squared. So your u is x squared. So u prime would be 2x. So you needed 2x here, but you have only 2. You have only x. So what you can do, as we talked about it before, you can divide the outside by 2, and you can multiply the inside by 2. Because these 2 would cancel out. You get the 1. You haven't done anything wrong. So then x e to the x squared dx. You see, this is going to be your u prime. If you put them together, it's going to be 1/2 integral of e to the x squared to x dx. You see? Quickly, this is simply what? This is simply du. So you have e to the u du. And integral of e to the u du is just e to the u. So it's going to be 1/2 of e to the x squared plus c, and you're done. This is, again, optional to get to know it because it's already there. It's like the one that you create here. You see, to get to the numbers, but it's optional. You can do it, you can do the substitution method in full, or just this is it. What you need a 2 here, create it. If you need the x, you can't do it, of course. But if you need a number, you create that number. So then you put the 2x and you see, this is it. U is x squared, and this is 2x dx, which is a du. So it's already e to the u du. You see, e to the u du. And e to the u du would be just e to the u, e to the x squared plus c. But again, it's optional to get these numbers done. Okay, so that's one format. I get to know it. The other format is that this e to the x can be given to in various form. For example, give you another one. These would be good for you, give you more experience to be prepared for the big one when we get to chapter 7. Another famous one is of this format, e to the x radical e to the x plus 1 dx. You have a couple of forms of this type of problems. So to integrate it, you know that you change the radical first. So solution is going to be, you rewrite it as e to the x plus 1 to the half dx. That's it. Anytime you get a power function, a parenthesis raised to something, you have to use the u substitution. So you take this one to be u, and you change it to the u to the half. Okay, so you take the u to be, you can do it by a short form, but let's do it. So u would be e to the x plus 1. You find the du, differentiate it. Lift of e to the x, just e to the x. Lift of x1 is 0. So that gives you e to the x times the dx. Okay, find the dx. So what's going to be the dx? The dx is going to be the du divided by e to the x. Go back and substitute and show that you get u to the half. Okay, so going back to the original one, that is e to the x plus 1 to the half dx is going to be equal to, you don't have anything for e to the x, don't worry. The inside, you call this one u, so it's going to be u to the half. And the dx, what's the dx? The dx is the du over e to the x. So e to the x and e to the x would cancel out. You get u to the half as you predicted. You see, that's going to be the one. Because that is the one that you predicted. And now action of integration, you add 1 to the power. 1/2 plus 1 would be 3/2 over the 3/2 plus the constant c. Use the reciprocal, that give you 2/3. U to the 3/2 plus c, you substitute. It's going to be 2/3. U, what's the u? U is e to the x plus 1 to the 3/2 plus the constant c, and you're done. Okay, so these type of integrations that you can use. Again, you can use the shortcut and do it in one line, really, because your prime is already here. So it's like u to the half. So the result would be e to the x plus 1 to the 3/2 over the 3/2. And then you're done. But it's okay to do the substitution in full. Just make sure you know it. Okay, and it can comes in various format. I give you another one. This is a very famous format, and we're going to use it quite a lot. So pay attention to this one. You may have it here. E to the x on the top. 1 plus e to the x to the 5th dx. See this one? Again, You know that this is a power function down the denominator. You move it up first. And when you move it up, that's the same thing as you did for the previous one. So we rewrite it as e to the x, 1 plus e to the x, everything to the negative 5 dx. That's it. So it's the same as the previous one. You see the power was 1/2. Now the power would be a negative 5. So again, your substitution method, this is going to be your u. So the u is going to be 1 plus e to the x. Differential of the u, du. Derivative of 1 plus e to the x is just e to the x. But you have to multiply by dx. You have to find the dx. So the dx is going to be the du over e to the x. Go back, substitute, you must end up with u to the negative 5. Okay, so take it here. Is integral of e to the x, 1 plus e to the x to the negative 5 dx is equal to, you don't have anything for e to the x, don't worry. 1 plus e to the x is u, so that can be u to the negative 5. And the dx is simply du over e to the x. Now e to the x and e to the x would cancel out. So that give you what? That give you integral of u to the negative 5 du. So the power rule, action of integration, you add 1 unit to the top, is going to be u to the negative 5 plus 1, which is a negative 4, over the negative 4 plus the constant c. We don't accept any negative power, so we bring it down. And this is going to be the sign of the fraction. So it's going to be equal to the negative 1 over 4u to the 4th plus the constant c. And you substitute. So they're going to be 1 over 4 u. What is u? U is 1 plus e to the x to the 4th plus the constant c, and you're done. Okay, so that gives you an idea of various formats of the integrations that we are going to have, just using this preliminary definition of the exponential function. Okay, so we have a couple of them on the problem that I assigned for you in 6.2. Quickly look at it. And I've already posted your practice quiz number 1. And you have a couple of them again on that practice quiz number 1. And there's going to be your first extra point. Okay, your first worksheet if you like, and you get some on that one. And then when you get to your quiz next week, first quiz, you will see a couple of them again. Okay, so that's all we need from this section 6. Okay, that was 6.2, exponential function and their derivative and integrations. Okay, so that's exponential function. Now we are going to give you the log function, natural log function, very important function for calculus too. Okay, all of them are so popular. That's why you want to make sure we are ready for it. Okay, so that's going to be 6.4. Introduction of that natural log function. Okay, so that would be the natural logarithmic function. Okay, that's one. There are different ways to define this one. There's one that we can use integral in calculus 2. In your book, they give you this one as well, but we just need one really. So we get to it right away, and then we are going to apply it. The introduction, you introduce it. Doesn't matter which method are going to use. Okay, so I'm going to use the kind of inverse function to introduce this one. And there is another section in your book, 6.4 star, if you like, that they introduce it using the integral. It depends how you read calculus, calculus 1 and 2. The way we teach at the university, we use a different version of your book. So we talk about these, we are going to have these functions right at the beginning of the course. But the way you do it, you are going to see it at the end of the course, Calculus 1 or in Calculus 2. That's why when you check the Calculus edition of your book, one of them is called Calculus Early Transcendental. When they say early transcendental, they mean they talk about the exponential function and the log function early, at the beginning of the course or in the middle of the course. But the other calculus, like edition of your book, they talk about it now. So they are not going to be early transcendental. Okay, but it doesn't matter. So we're going to say it here. So it depends. If you want to do the early, this is the definition. If you want to do the late, you have to go through the integral and you don't need it. Okay, there you are. And so I'm going to introduce the log as the inverse function of the exponential. So again, if b is going to be, if b is a positive number, must be positive. Positive number with b not equal to 1. That's 1. Then a log function. Okay. A logarithmic function. Function again with base b is going to be defined by or introduced, is denoted, if you like, denoted by f of x equal to f of x is going to be the log of x with base b. Okay, and it's going to be defined and is defined by, we define it by exponential function. It's the way we do it. Say that the y is equal to the log of x at base b if and only if we switch it. X is equal to the b to the y, b exponent y. See, in this form, this is going to be the inverse function. You know that if you switch the x and the y, you're going to have the inverse of the given function. So we define the log function as the inverse of the exponential function. Since we already talked about the exponential function, so we can relate any information for or any information of the log function to the exponential function. And we already all the information of the exponential function, so we can get the log quickly. Okay, so that's going to be our definition that we are going to have. Now a couple of notation quickly, the way we're going to do it. If this base, if b is 10, we don't write it. If b is going to be 10, then the log x at 10 with base 10 is going to be called the common log. It's called the common, usual, common log function. Okay, logarithmic function, and is denoted by the definition. We don't usually write the 10, log x at 10, it's just simply log x. So if you see log x, you should realize that this is the common log. The base is going to be 10. Now, if you get this one, the definition would be, so in this case, y would be log x, if and only if x would be the base, 10 to the y. So that would be the definition of your log function. Okay, the base 10 is popular, the common log. The base 2 is binary one and used in computer science. But the base, of course, that we are going to be interested in is the e-base, the one that gives us a natural exponential function. Okay, so we focus on this one. If b is going to be equal to the e Okay, Euler constant, some people call it Neperian number. Okay, if B is equal to the E, then that the log with base E is going to be called the natural log. It's called the natural. We get the natural log function, logarithmic function. And we have a special notation for it, okay? And it's going to be denoted by and is denoted by the log of x at base E. We simply write a ln x, natural log of x. Okay, you must know it and you must be able to, okay, locate it on your calculator. Depends which calculator you are going to use. So for example, this is the one that I have. You will see this is ln, and the other one is going to be, okay, the log function. So you should locate it on your calculator because we're going to use it from time to time. When it's application problem, you have to find it for us. Okay, so it's going to be ln function. So the definition in this case is going to be, so the definition is going to be y equal to the ln x, natural log of x, if and only if x is equal to the base is e to the y. Okay, that would be the natural exponential function. We are going to focus on this one because anything else we can change it. And since in calculus, basically you are interested in, okay, in the derivative and the integral of this type of function, so it's going to be easier to work with this one. You will see that, you know, if you know this, you can find the integral and derivative of the other function too. But it seems to be messy when you want to write it down. I'll show you at the end. Okay, so from now on, this is going to be the one that we are going to be interested in. So let's check to see if it's the property of this function. Okay, so we'll check some properties. There are some algebraic properties we are not interested in. You know it from your pre-calculus courses or college algebra course. So we just focus the one that's going to be related to our job. Okay, so what's going to be properties of this function? F of x equal to the ln of x, natural log. Anything you want to know, you go to the other side to get to know it. The most important part is the domain. Domain of this function. Domain, you know that. What can you assign to the x? So where the x is coming from here. So x is in the range of the e because it's the result of the c. X is e to the something. But e is a positive number. And e to the whatever is positive. So x must be a positive number. So this means the domain of the log function is positive numbers only. 0 and positive infinity. That's it. Okay, if you check ln -2 with your calculator, the calculator will give you an error. So we cannot find the ln of a negative number. Of course, nothing is impossible in mathematics. ln of a negative number is going to be a complex number. But over here in calculus, there is no complex numbers. So that's why we just focus on this one. Okay, if you are measuring physics or electrical engineering, sometimes you need to have a ln of a negative number. Then you have to use a complex, okay, complex numbers. But for the calculus, you have to go over calculus 1, 2, 3 first, then come back. Come back and talk about, you know, the ln function when x can be a complex numbers. Again, if you are measuring in particular physics, you are going to have another calculus course. They call it mathematics for physics or mathematics for engineers. That's a kind of advanced calculus. It's going to be a calculus on which you can use complex numbers. But that would be different, quite different story. So in this course, the domain of the ln function is positive numbers only. So You cannot use ln of 0, or you cannot use ln of a negative number. Okay, so it's going to be domain. Second one is the range. Range is the output, the y. Y is the exponent. You know that the exponent of the e can be anything. So the range of the log is going to be negative infinity and positive infinity. So this means any number you think about it is going to be ln of something. Okay, so the domain is going to be positive numbers, and the range is going to be all real numbers. Some other properties, number 3, ln of 1. You can check it with your calculator or just see it over here. You want the x to be 1, so e to the what is equal to 1. You know that e to the 0. So ln of 1 is 0, or you can check it with your calculator. That's famous. We are going to use it from time to time. And the other one is ln of e. Ln of e, so x is e, x is e. So e to the what power is going to be equal to the e to the 1. Again, you can use your calculator. Anything else, your calculator. Okay, but these two are going to be famous, and we're going to use it from time to time. But anything else, you want to find the ln2, just using your calculator to get the ln2, you know it. Okay, you know it, and we are going to use it. So for example, this is going to be ln, you see ln of 2. I close parentheses, and that should give me, okay, so that should give me 0.69. 0.69 is going to be ln2. Okay, so if you need it, we can use calculator to find it for any other numbers. Of course, for the positive numbers. Okay, so it's going to be 1, 2, 3. Some property of the ln function that uses from algebra, but we focus on the one that we use for calculus. Okay, so for the calculus, remember I talked about the limit of e to the x for you. So we have these two famous limits that we're going to use in this course. The limit of ln of x, and when x goes, you see the domain is 0 and positive infinity. When x goes to 0 positive, 0 positive. So the ln is like the exponential function, is increasing function. So the number is getting bigger and bigger and bigger. So when it goes to 0 positive, that's the beginning of the domain. So the result would be like the beginning of the range. So that would be in negative infinity. We're going to use it in a couple of places, so make sure you remember it. Okay, limit of x goes to 0 positive, this is it, 0, negative infinity. And at the end, so if you want to find the limit of ln x, when x goes to positive infinity, is increasing, the positive infinity goes to positive infinity. Both of them are going to be used when we get to section 7.1, and in particular in 7.2, and when we get to the series. So make sure to make a note of these two, and then that will help us to graph the ln function. Again, if you need more points, you can use your calculator, but that would be enough. Ln of 1 is 0, so we get the intercepts here. At 1, when x goes to 0 positive, ln is negative infinity, so start from here. X goes to positive infinity, and that would be a positive infinity. Okay, so we just pick some points that give you the graph of the ln function. Okay, so the domain is going to be 0 and positive infinity. So as you go on, it's getting bigger and bigger, up, 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 up. That gives you the graph of the ln function. Okay, more information, you can use your calculator to get more points. But we need it to have, sometimes we want to get a justification of whatever we do. So we refer to it, just make sure you remember it. Okay, so number 5 is the one that we are interested in. What's the derivative of this function? Most popular, very popular function for differentiation for the rest of the course. Okay, so number 5, let's say this function is differentiable. Okay, so the function. Okay, that's going to be the function f of x equal to the ln x is differentiable. And derivative of this function, just 1 over x. So formula to remember, derivative of ln x is 1 over x. Okay, it's going to be 1 over x. Of course, you know that x is positive. And in general, if you have anything other than the x, you can use the chain rule. In general, if u, as usual, equal to the u of x is a differentiable function. Differentiable function, then you have to apply the chain rule. If of the ln u you see, for the chain rule now you have two functions, ln function and the u function. According to the chain rule, it's going to be the derivative of the ln function. The derivative of the ln function is just 1 over u. And you have to pay for it, times it by the derivative of the u, which is u prime. We write it down as u prime u, very famous formula. So derivative of ln u is simply u prime u. Very famous for calculus 2. Okay, and that's going to be the case. I'm going to give you a proof because the way your book is prove it in section 6.4 prime, they just use the idea of the integral, but it can be done really easily. Just for your information, just to see how easy it is to prove this derivative. You see, look at this one. If y is equal to the ln x, then definition. Remember, y is ln x. This means x is e to the y, because the base is e. Differentiate. If you differentiate both sides respect to the x, okay, so it's going to be x equal to the e to the y. If you differentiate it, the derivative of x would be 1. The derivative of e to the y is like e to the u. Is derivative of the e function e to the y times y prime. Okay, you can take it as exponential, as implicit differentiation, or just a chain rule. So y prime would be what? Y prime would be 1 over e to the y. But e to the y is x. E to the y, you see, e to the y is x. So y prime would be 1 over x, you see, very easy. So what I did, I proved that the derivative of ln x is simply 1 over x. Very easy proof, much easier than the one you have in your book in section 6.4 prime. In that case, they just use the notion of the integral. This is what we do when we use the when we do it in calculus 1. You know, we do it just at the beginning of the course. But anyway, just make sure you know the formula. But if you are interested in proof, this is easy proof to remember. Okay, and the chain rule 1 would follow quickly. So derivative of ln x, 1 over x. Anything else? Derivative of ln u, u prime u. Okay, so that would give us a very nice formula. So not only for the differentiation, but quickly we can change it to the integral. So if you want to have it in integration form, that's it, equivalently, if you want to find the integral of 1 over x dx. You see, if you move it up, that gives you x to the -1. You cannot use the power rule, because -1 plus 1 would be 0. So you want to find a function whose derivative is 1 over x. That function is ln x plus c. But there is a catch here that you got to be careful when you write it down. You see, the domain of these two functions must be the same. must be consistent when you write it down. 1 over x, the domain is all real numbers except 0. ln x, you know that domain is all positive numbers. So they are not going to be the same if you write it down as is. So what we do to repair it, we just use the absolute value of x rather than the x. The result stays the same, but you must use the absolute value, otherwise it doesn't make sense, okay? So I repeat it again. So the domain of these two functions must be the same. The domain of 1 over x is everything, means positive or negative numbers, except 0. But the domain of ln x is just positive numbers. So you must make sure that the domain are going to be the same. So if you put the absolute value here, now we can say it. The domain of this function, all real numbers except 0. And the domain of ln of the absolute value of x is again all real numbers except 0. So make sure that you put that absolute value around it. Okay, the chain rule type, of course, if it's going to be 1 over u, so we have to have the du. The same thing. A very, very popular formula for calculus 2. Okay, so that is going to be the advantage of this formula. That's all you need to know, and very important to know it and be able to apply it for the natural exponential function. Okay, I'll give you some example. You should be able to differentiate again for us and integrate it. One question on the quiz. Okay, so you already got 2 questions from the quiz. So that's it. Example, first differentiation. Find the derivative of each function. Nothing complicated, just 2 format. Derivative of each function. The format are straightforward. These are the one that we're going to be interested in really. So this is the one that's going to be used from time to time. The power of x times ln x is going to be a product of 2 functions. The first function is 5x cubed. The second function is ln x, so you have to apply the product rule again. You see the product rule? First, second, derivative of the first times second plus derivative of the second times first. That's it. So the derivative of the first one, 15x squared, times the second one, ln x, plus derivative of the second one, derivative of ln x, 1 over x, times the first, and you have to simplify it. Okay, so the solution is going to be f prime of x is equal to, of the first one, 3 times 5, 15, 15x squared, ln x, plus derivative of the second times first, derivative of ln x, 1 over x, times first, times it by 5x cubed. You're not done. You have to simplify it. So simplify these two. So f prime of x is equal to the 15x squared ln x plus 5x squared. And you're done. Again, you cannot do anything about it. Don't try to simplify. It's not possible. You have to simplify this part only. Okay, so it's very popular. We are going to use it. X to the third, to the fourth, to the fifth, to the sixth. This is what you are going to see for the rest of the course. So a product rule, no chain rule is going to be involved. Of the first one, 15x squared times the second, ln x. Of the second times first, if of ln x, 1 over x times the first. But you have to simplify. Okay, that's a ordinary type. The next one is going to be the chain rule type. G of x is going to be ln of something, something like x cubed plus 2 sine x. So it's not ln x, it's ln something else, so you call it u. So remind yourself that you want to find the ln u, derivative of ln u, simply u prime u. Okay, so the solution is going to be g prime of x is going to be equal to u prime, lift up the inside, 3x squared plus 2 cosine x divided by u, x cubed plus 2 sine x. And you're done. You see, I've seen some people try to do something about it. You can't do anything about it. And it's done. You cannot simplify it. And you don't suppose to. Okay, so simply it's ln u, and you just give us the answer. It's going to be u prime u, and be done. Okay, so that's mostly the derivative that you need to know for when you change it. These type of problems. Okay, so we give you one. Now integrations, much more important version. So we want to find evaluate each integral. Evaluate each integral. Again, it's going to be very popular form. The first one is going to be integral of, that's it, 1 over 3x plus 5 dx. You see, as a rule, if there is a parenthesis here, raised to something, you move it up. If there is no parenthesis, no power, you stay where you are. You take this one to be u, you have to change it into the 1 over u du, ln function, okay? From now on, for the rest of the course. If you get a rational function, you get the 3x plus 5 here only, okay? You take this one u and you look for the u prime on the top. In future, it can be done quickly because if you take u, this one, 3x plus 5, u prime would be 3. So we can, 1/3 and 3, we do it right away. But for the time being, I just go through it. So stay where you are. Take the bottom one to be u, 3x plus 5. Find your du, which is u prime. U prime is going to be 3 dx. And find the dx, which is the du over 3. Usual substitution method. Go back and substitute. This is going to be 1 over 3x plus 5 dx. So it's going to be 1 over 3x plus 5 is u. Now the dx is the du over 3. Nothing to simplify. There is a third extra, put it out. So that give it 1 over u du as you predicted. Okay, 1 over u du ln of the absolute value of u. So it's going to be 1/3 ln of the absolute value of u plus c. Substitute 1/3 ln of the absolute value of 3x plus 5 plus the constant c, and you're done. Okay, it's very a standard operation. You can't miss it. But it is very popular, and we are going to use it quite a lot. Okay, so when there is a parenthesis here and there is a power, you move it up. But when there is not any parenthesis here, it can be done by the natural log. So you are going to say, change it to the 1 over u. You take the u to be 3x plus 5, and then you look for the u prime dx and substitute, get the result. The short form also can be used. You need the u prime on the top. Let's check these short terms because this is going to be very popular really. And if you can use it, we don't mind. So the short form, shortcut, you see you already got the 1 over 3x plus 5 dx. You need the u prime on the top. You see if you get the u prime u, you know that's going to be natural log. U prime is 3. So you need the 3 on the top. So you write as a 1/3, 3x plus 5 dx. You see? So what you have over here, this is u prime. That's u. That's u prime. You know that u prime u is the derivative of ln u. So this is going to be simply 1/3 ln of the absolute value of u, 3x plus 5, and c, and you're done. Okay, so that's going to be easy method, and we are going to use it because that's, it's going to be used quite a lot. But if you like it, don't like it, you go through this. Okay, so you need u prime on the top because the derivative is, look at this one, u prime u. U prime u is the derivative of ln u, derivative of the denominator. So that's exactly what would happen here. So the bottom one is 3x plus 5. So the u is 3x plus 5. U prime is 3. 3 is a number. So multiply the top by 3 and you divide the integral by 3. So you make it even. You balance it. Now you have u prime u. So the result is going to be 1/3 ln of the absolute value of a denominator, 3x plus 5, and you're done. We accept it if you can apply it. And and we encourage you to do it, if you can. So that's going to be 1. So another one, this format is again popular. Okay, they give you something like on the top, let's say secant squared, and on the bottom is going to be 1 plus tangent. You have a various format of this one. Sine x over 1 plus cosine, cosine x over 1 plus sine. So what you are going to do really is, this is, again, you are going to consider this one to be u. You see, u prime is on the top already. So it's a u prime u. It's going to be ln of the denominator, done. But if you want to go to the short, long format, you take the u to be 1 plus tan x. You have to find the du. Derivative of 1 is 0, derivative of a tangent secant squared. dx. You have to find the dx, which is a du over secant squared of x. Go back, substitute. So what we have? Integral of secant square of x, I rewrite it. 1 plus tan is going to be equal to, we don't have anything for the secant square of x, don't worry. 1 plus tan, we already call it u. And the dx is the du over secant square of x. So these two would cancel out. The top would be just 1, so it's the integral of 1 over u du. And you know that this is going to be ln u. Ln of the absolute value of u plus c is going to be ln of the u. What is u? 1 plus tan x plus the constant c, and you're done. Okay? And the short form, encourage you to use it. You see this one? You take this one to be u. You look for the u prime. What's u prime? You have 1, 0. You have a tangent secant square. So u prime is on the top. So it's a u prime u. U prime u, the result is ln of the absolute value of u. Absolute value of u would be 1 plus tan x plus c, and you're done. And we accept it. Okay, that would be popular to be able to identify it because it's already there. Okay, and you don't need to go through this format. But if you go through it, we don't mind. Okay, now you must pay attention to the next 2 examples that I'm going to give you. These 2 examples are going to be coming with you all through this course. So you may see it in your quiz 1, test 1, test 2, test 3, and even the final. because there are various topics that would be related to the following two examples. Okay, so pay attention to get these numbers. We have a various format. Okay, this is it. This is one of them. You see, this is one format, ln of x, everything to the fifth over x dx. It's going to be power of the ln over x, or that power may be on the denominator. In future, we have something, we call it sequences, series, improper integrals. On all of them, this would be used. Now we're going to find it, substitution method, of course. This is the power function to the fifth. As usual, you take the inside to be u. And you have to show that this would end up with u to the fifth. Very easy. The u to be ln x. Find the du, derivative, 1 over x dx. Cross multiply to get the dx. Multiply by x, so the dx would be x du. Okay, it's a power function. You expect to change it to the u to the fifth. So take the u to be ln x. Then you have to find the dx. The du would be derivative of ln x 1 over x dx, and the dx you cross multiply. Go back, substitute. So it's going to be ln x to the fifth over x dx, which is ln x. Ln x is what? Is u to the fifth. X, you don't have anything for the x, don't worry. The dx is x du. Is like, you know, x dx over 1. Now the x and x would cancel out. So that gives you u to the fifth du. See? Which is going to be, of course, u to the 6 over 6 plus the constant c. You substitute for the u, it's going to be ln x to the 6 over 6 plus the constant c, and then you're done. It's a very easy integral, but it's very important one. What we are going to do in future is there's going to be improper integral. Improper integral is going to be something like 1 to infinity here. So the way we do it, we integrate it first, and then we take this limit, we take the limit of this function when it goes to positive infinity. And I've already talked about it, that the limit of ln x when it goes to positive infinity is positive infinity. I told you it's important. Positive infinity. When we get this a number positive infinity, we say this integral diverges. If this limit is going to be anything other than the infinity, we say the integral converges. So that's why we use this one. So we don't like this one because we get a positive infinity. But there is another version. Okay, so it's nothing in particular. This is 5, it may be 6, 10. As long as this is going to be a number bigger than 1, the result is the same. Then we are going to have something, we call it in future P integral. We call it P, and there are a theorem related to this one. That's why I tell you that this is going to be used 4 times at least through this course. Okay, so just pay attention to this one. And of course, you have it in your that practice quiz, your assignment that I posted, your take-home one, that worksheet that we talk about it, and probably you will get one of them on your quiz. So pay attention to this. Now, the way we like it in calculus in later on is when this is done here. So this is another format, much more popular. So the 1 over x ln x to the 4th down the denominator. The solution is going to be the same. You take the u to be ln x again. Okay, you know, the first part is the same. You have to find the du. Derivative of the ln x is 1 over x dx. You do the cross multiplication, dx would be x du. Okay, that's the case. You go back and substitute. The last part's going to be different. And that's ln x to the fourth dx. You substitute, there's going to be 1, and this is going to be x. Now it's going to be u to the fourth. U to the fourth and the dx. And what's a dx? dx is x du. The same thing that we did for the other one, but you see the leftover is going to be what? Is 1 over u to the fourth du. In the previous one, you get u to the fifth, the positive power. But for this one, u to the fourth is down the denominator. Of course, you have to move it up. So when you move it up, it's going to be u to the negative 4 du. When you integrate, it's going to be u to the negative 4 plus 1 would be negative 3 over negative 3 plus the constant c. So this is going to be 1 over, this is going to be negative sign, it's going to be negative 1, 3u to the third, okay, plus c, and then you substitute. It's going to be negative 1, 3 ln x to the third plus the constant c. That would be the final answer. Why we like this one? Because when you take the limit when x goes to positive infinity, the denominator would be infinity, so this would be 0. When it's a 0, they say, oh, integral converges when we get to the second part of the course. And that's why they like it. So they don't like the first one, and they love the second one. But you are going to have both of them, okay? So get to know it, because it's going to be used, as I told you, 4 times, I promise you. 4 times during this course, you have to find this integral for us. Both of them, 3 and 4. Okay, so pay attention to this one, and then you'll be fine. That's all we need for that section, okay, 6, 2, and 4 of your book that I summarized it for you. So check the assignment that I gave you on this section, 2 section. If any difficulty, let me know, and you should be able to find this, do quite a lot of those integration that I gave you as a substitution method. A number of them would be need, you need this idea of the ln function to be able to take care of it. So go over it. If you have any question, just let me know. The only other section that we're going to cover is going to be, I think, maybe 6.6 or 6.8. It's inverse trigonometric function. Okay. So I post another lecture for you during the week, okay, maybe by Tuesday, which is going to be inverse trigonometric function. So that's where we get to the first quiz, okay? So discipline yourself to these 3 sections for the first part of the course, and you'll be fine. So we hope to give you the quiz, the quiz is going to be next week. I think that's one. You know that your quiz is going to be take-home quizzes. So I post the quiz, and then you submit the quiz through the Canvas. But your test is going to be on Zoom. So we hope to be able, the target is to be able to finish this one. We are going to finish it next week. So we collect the assignment as we post it, then be able to get to the chapter 7. But these 3 sections are very important, really. That would be very helpful for you. So get to it, go over it. If you have any difficulty, question, just email me. If you need any office hour, again, email me. Then we can arrange it on Zoom to be able, to take care of it. Okay, and anything else, just let me know. Okay, I'll post this one quickly so we can have a look at it. Have a good one and take care. Bye-bye.